Okay, so good morning, everybody. Okay, so review. Okay, so is this okay to have a review class? And why does nobody other than Sai turn their videos on? I don't know. Like, if you can, if you are able to, and if circumstances permit it, it's nice to have people with their videos turned on so I can see some sort of, this can be some sort of interaction between, but anyways. Okay, so what is the basic structure in relativity, right? The structure in relativity is a vector space, which is called Minkowski space. It has 4 coordinates. On this space, we can define a metric which measures distances between points. And this metric, so can be understood as, for instance, you in 3 dimensions, you have your normal Pythagoras theorem. Pythagoras theorem tells you that if you take a vector, you can calculate the length of that vector, right? In Cartesian coordinates. This is true in Cartesian coordinates. And that if you take any 2 vectors, let's say in this case, this x and y, then you can calculate the length, the displacement between these 2 points, right? The distance between these 2 points as the length of the vector connecting the tips of x and y, right? So that is this quantity, delta r. Now, so all of these expressions can be written as follows. They can be written as, whenever I have the length of a vector, it can be written as in this way, delta I jx ix, right? And this quantity, this delta, this is called a metric. So metric is the technical expression for it is that a metric is what is called a bilinear form. So if you know, a metric is a bilinear symmetric form on a vector space. So what does that mean? Bilinear. So if you look at this expression is linear in xi and in xj separately, not together, but separately. Symmetric means that, well, this matrix is symmetric. If it was not symmetric, then, for instance, if you calculate the distance between any 2 points, the distance would depend on whether you go from A to B or from B to A, right? And obviously, like, again, that doesn't match with our understanding of physical intuition. So we have a symmetric, and form just means that, well, it's something, it takes in some vectors and spits out a number. And then we have a very important tool which is called the Einstein summation convention. And basically what it means is that whenever you have these dot products or other such objects, you just leave out the sum symbol, right? Whenever you have repeated indices. So whenever you have repeated indices, it is understood that there is a sum. So if I want to write u dot v, I can just write it as ui vi. The fact that the I index is repeating twice means that I'm summing over that index. So if I want to look at this expression for the length of a vector, then I can write it as x squared, the length squared is equal to this expression. Now there are two indices, there is an I index and there's a J index. Both of these indices are repeating. So it's understood that these indices are contracted. So that the technical terminology is, we say that when two indices are summed over like this, we call it index contraction. And so whenever you have two indices on the right side, on the left side, those indices are not present because they have been summed over. So they are also known as dummy indices. Because in this expression, instead of calling it xi, I could call it anything I want. I could have called it delta AB, xa, xb. I could have called it delta. I mean, I can use anything. I can use a letter from the Hindi alphabet if I wanted to, or the Kannada alphabet, right? Something like this, and then I mean, I don't really know whether these are real characters, but close enough. The point is that I can use any symbols. These are, so that's why we call them dummy indices. So this convention we can use for all sorts of linear algebra operations like matrix multiplication and so on. So matrix multiplication, we have this kind of a so matrix multiplication means that, right, you're summing over this internal index k. So I can just write it in this way. So that means this Cij is equal to this quantity. But sometimes there will be cases when we don't want to sum. So we have to just be explicit and specify. For instance, if I want to refer to the diagonal element of a matrix, that is Cii. Now, if I write Cii without specifying, then what does this Cii mean? It means the trace of the matrix C, the sum over the diagonal elements. So if I just want in some expression to say the diagonal element of C, I should specify on the side, make a note. Similarly, for instance, the product of a matrix and a vector can be written using this convention in this way. Okay, now when we are in Minkowski space, we have four indices. Those four indices are generally labeled in terms of Greek lowercase letters, which go from 0 to 3. So 0 is conventionally for the time index and 1 to 3 is for the spatial index. And on this four-dimensional space-time, the same way that on the three-dimensional space, we define a metric as the length of a vector, here also we can define a metric as the length of a vector or the dot product between two vectors. The difference is that the time component gets a negative sign. So it's basically a dot product, but all the signs are positive except for one, which is negative. So this expression you can easily check can be written in terms of this matrix eta mu nu. This eta mu nu is called the Minkowski metric. Right? So the dot product between any two four vectors is written in this way. Then, and if you are uncomfortable with raising and lowering, just work with indices all lowered or all raised. I don't care. Okay, like for your purposes, just use whatever convention is suitable or it's easiest for you to follow. Okay. So these are all just various examples of index contraction. Then there are some instances when you have, for instance, matrices which are multiplied when the order matters. So if I take the product of two matrices, it depends on whether I take one matrix first or the other. But when I write this product in terms of this index notation, So this Cij, Aij, Bkj. Now in this expression on the right side, these are both numbers. So if I switch them, if I write B kj and I second, I get the same answer. So one of the benefits of the index notation is that you don't have to worry about the order of elements. Okay. Right. So finally we come to the concept of a 4 vector, and a 4 vector is defined in this way. If you look at the vector x mu is written as x0, x1, x2, x3, and its dual vector. So this is the dual of the vector. So this is a vector, and this is the dual vector. The dual vector is written as this. So you get a minus sign on the time component. Now this dual vector can be expressed in the following way. You can write it as eta mu nu x nu. This is called raising an index. You have raised this index. So when you take the inner product of two vectors, you have to multiply the dual vector with the vector. And when you do that, you get this. So this is called the Minkowski or Lorenz inner product. And you can see that immediately that this is different from the Euclidean inner product. So the Euclidean inner product is what? Euclidean inner product is when I just have 3 indices, right? All spatial indices. So the Euclidean inner product is always positive definite. It is always either it is 0 when the 2 points are the same, or it's greater than 0. But this 4 vector, this Minkowski inner product, because of this negative component, it can be either negative or 0 or positive. So you can understand what these different things mean by drawing something called a space-time diagram. So in a space-time diagram, the horizontal axis represents the position, the vertical axis is the time. And to make the dimensions of both of the axes same, we multiply the time by c, speed of light. So you get something which has units of distance. But by convention, we set c is equal to 1. And remember, this is just a choice of units. You can always set c is equal to 1. What does that mean? Let me just clarify this for 1 second. You'll say, well, how can you do that? C is 3 times 10 to the 8 meters per second, right? That's what I say in my MKS units. But when I say that, what is 1 meter? 1 meter is defined as some length, right? I mean, some collection of atoms or something like that. It's defined as some reference, right? So I can define a new unit of length. Let me call it one light meter. And let me call that 3 times 10 to the 8 meters. So then what is C? C is equal to 1 light meter per second. So it's equal to 1, no issues, right? So this is always just a choice of units. I can always do that, okay? Then in this space-time diagram, you can draw 3 different kinds of lines which have a slope less than 45, equal to 45, and greater than 45. Lines which have a slope less than 45 correspond to objects which are traveling at a speed greater than the speed of light. These lines correspond to something traveling at the speed of light, and this is less than the speed of light. And why you can see that this is the speed just by taking the slope between any 2 points, and that slope is equal to 1 over the velocity. Then you can use this concept to understand what is known as causal structure. So causal structure means what points in space-times have an effect on other points in space-time. So if you look at the origin in this space-time diagram, and you imagine that there is something that happens at this origin, that something, whatever that information is, it will get outwards, right? But it cannot propagate at a speed greater than the speed of light. So anything that happens here, it can only move outwards at a maximum speed of c in this direction and in this direction. Well, actually, it's in all directions, but in this projection, you can't tell. So any point within the green region over here, any point within the green region can receive a signal from this origin, but any point in the red region cannot receive a signal from the origin. So we say that the points in the green region with respect to this point are space-like separated. Points along the yellow lines are light-like, and points in the red region are space-like. But this applies only with respect to this point. The moment you look at a different point, that point will have its own causal structure, right? So when you say that you don't say a point is space-like, you say that the separation between 2 points is space-like or time-like or null. A point by itself is not either space-like or null or time-like. Then we come to Lorenz transformations. And Lorenz transformations can be written in this way, right? So Lorenz transformation is a linear transformation of the coordinates of time and space. And we can rewrite this by defining a quantity called beta. So that's the rescaled velocity, v by c. And we can rewrite the Lorenz transformation, this expression, by writing down this Lorenz factor and multiplying the time by c, so that you are using time in units of distance, right? The relativistic units. But when you multiply time by c, you have to divide v by c. And so here, for instance, you get beta. So x prime becomes gamma x minus beta gamma, and then ct. But then setting c is equal to 1, this just becomes gamma x minus beta gamma t. And similarly, t prime becomes, whenever I write t, it's understood, whether it's t or t prime, that there should be a factor of c in front of it, becomes this expression, minus beta gamma x plus gamma t. So this can be written as a matrix like this, where the components of the matrix are this. So this kind of a matrix is called a Lorenz transformation, and it's an element of something called the Lorenz group. So such matrices, they form a group. What is a group? So a group, let me just go to the group part first. Where is it? A group is a set which has two operations, which are called, well, it has one operation, which is multiplication. And the elements of the group are closed under that operation. That means if I take any two elements and multiply them, I get another element of the same group. So where is that? Yeah, groups and symmetries. And then a group also has an inverse element and an identity element. So these Lorenz matrices, and there are other examples of groups which are called translations, the group of rotations, and the group of boosts. Boosts are these Lorenz transformations. Together, the rotations and boosts constitute what is called the Lorenz group. Actually, it constitutes a certain component of the full Lorenz group, which is called it's written like this, SO31 plus. It's called the positive connected component of the Lorenz group. So, Well, there's a lot of material here, and obviously I can't review all of it. So let me go back again to some of the things that I skipped here. So these Lorenz transformation matrices for 4 vectors can be written in this way, right? And since nothing is happening in the y and z directions, I just get identity there. And there is a certain convention for raising and lowering indices, which I have explained here. Again, you should go back and revise this, obviously. If you don't understand it, tell me, ask me, I'll explain again. So when you apply a Lorenz transformation on a 4 vector, the new vector can be written in this way. So this is exactly the same as applying a rotation to a 3-dimensional vector. What do? You have a rotation matrix, you multiply it by a vector, this vi, you get another vector. And when you do this multiplication, it's a linear algebra operation. So there are 2 indices which are summed over. So we again use the summation convention. Now, what is this Lorenz transformation? It's a coordinate transformation, right? You're going from one set of coordinates to another set of coordinates. So in general, whenever you have a coordinate transformation, it can be a linear transformation or a non-linear transformation. For instance, you have this relation between the spherical coordinate phi and the Cartesian coordinates x, y, z. So this is obviously a non-linear transformation. But regardless of whether it's linear or non-linear, one can define this quantity, which is called the Jacobian. So you basically are taking the derivative of the new coordinates with respect to the old coordinates, right? So each of these new coordinates, t prime, is a function of the old coordinates. T prime is a function of px, y, z. X prime is a function of px, y, z, like this. So this matrix, the Jacobian elements, are simply the partial derivatives, like this. Dx prime, dx, dx prime, dt, and so on. So if you just look at the Lorenz transformation, you can read off these Jacobian elements just by taking the partial derivatives. And you get this expression, which we have already seen. Now, the inverse of a Lorenz transformation corresponds, according to relativity, as simply the same transformation, but for a negative, for the sign of with the sign of the velocity changed. So minus beta just becomes beta. And so you can easily check that when you multiply this matrix by another matrix, which is the same except for this negative sign is not there, you get the identity matrix. Okay. Now this Lorenz metric and the Minkowski metric has some very nice properties. What are those properties? Well, we can write down this quantity, which is the Lorenzian distance or the Minkowski distance between any 2 space-time points. And like I said, it can either be null, space-like, or time-like. What is nice is the fact that under a Lorenz transformation, what will happen? My points, the coordinates of the points will be changed. X mu will become x mu prime, y mu will become y mu prime. And so when I look at this distance, this quantity, right, this is a number. First of all, this distance will not change under a Lorenz transformation. This is something you must know. You should know, okay? The second thing is that since this distance doesn't change under a Lorenz transformation, that means if it's negative in one frame of reference, it will always be negative in another frame of reference. If it's 0 in one frame of reference, it's 0 everywhere. So that means that whenever I take 2 points, those 2 points, if I say they are space-like with respect to one observer, then that means they are space-like with respect to all observers. And this also means that when I look at a moving observer, which is this green line in the figure on the left, and I ask what is the light cone of the observer moving along this green line, then the light cone, you might think naively, is given by this by these lines rotated by an angle of 45 degrees. But because this distance is preserved, right, what that means is that if I have 2 points which are on the light cone, that means on these orange lines in the O frame, these 2 points will continue to be along the orange lines with respect to the O prime frame. So this light cone does not change under Lorenz transformation. It remains the same. Then we can take the product of 2 Lorenz transformations to get a third Lorenz transformation. This can also be used to derive the velocity addition expression. And we have another consequence of this Lorenz transformation is that this metric eta mu nu, it remains invariant under the Lorenz transformation. So now vectors transform under Lorenz transformations in this way, and matrices transform under Lorenz transformations in this way. For each index, you have to put one Lorenz transformation. And this metric happens to be an invariant object under these transformations. Then, I have all this material on passive and active transformations and so on and so forth, which is all quite basic. So I'm not going to go over that. And this again, so then we come to groups. In groups, there are different kinds of groups. There are discrete groups, finite groups, and infinite groups. And I think in one of the homeworks, I've asked you to give examples of all of these. So you should be able to give examples of each one. So the Lorenz group and the rotation group, for instance, in 3 dimensions are continuous groups. They are infinite groups, right? So then I talked a little bit about symmetries and how, for instance, the Hamiltonian acts on some system. So that means that this Hamilton, if something is conserved, that tells me that so momentum is conserved. So that tells me that momentum is a symmetry of the system. Okay. So yeah, I gave you this in a homework, so you should know how to do this. Then SO3 is the group of rotations in 3 dimensions. SO31 is the group of Lorenz transformations in 4 dimensions. And again, you should know what these different terms mean, SO, and 3, and you should know why, what is, so S means special, which means determinant +1, U means unitary, O means orthogonal. So you should be able to explain why, what is the requirement of orthogonality, why is that needed, so on. Okay, so then, like I said, I gave you a homework problem. I'll try to correct your first homework assignment before Sunday, so you can have it as a reference. But I can't promise that I will get it done. Then, this is very important. You can write down your Lorenz transformation in terms of an angle. This angle is called the rapidity. And so you can write down these two quantities as, excuse me, as hyperbolic cos and hyperbolic sine. So the Lorenz transformation can be written as it looks like a rotation matrix. Only thing is that it's not a regular rotation, it's a hyperbolic rotation. And okay, so then we come to the concept of a tensor. What is a tensor? All right. So you have a scalar, which is a rank 0 tensor. You have a vector, which is a rank 1 tensor. Then you have this matrix, which is a rank 2 tensor. And how do tensors transform under coordinate transformations? So you might think that, well, is any matrix a tensor? And the answer is no. In order to be a tensor, a matrix has to have this. In order to be a tensor, a matrix has to have this transformation property, which is that upper indices and lower indices, they transform in a certain way. So these are called contravariant and these are called covariant indices. And upper indices transform according to the Jacobian. Lower indices transform according to the inverse of the Jacobian. Okay, so this is all like definition. But then you can actually explain why this transformation should have this form by looking at a physical situation. For instance, I gave you this example of currents in some material. And these currents are generated due to the application of some external electric field. Now, in an arbitrary system, you can have anisotropy. Sorry, I don't know why I'm yawning. Maybe the material is too familiar to me, so I'm boring myself. I hope I'm not boring you. Probably am. If I am, you can turn your video off and go to sleep. Take a little nap. So, in the isotropic material like this, you can write down the response that is created in any direction. So you can say that Jy is the response in the y direction due to an electric field in the x direction. So you can define this object, which is the conductivity. So this conductivity is written as sigma yx. So if you look at the very general case that you have an arbitrary electric field and the result is some arbitrary response, then the relationship between these objects can be written in this way. And this is nothing but a linear transformation, which is a matrix, which corresponds to a matrix. So this transformation can be written as this vector J, the response is equal to this matrix multiplied by the electric field. This matrix is called the conductivity tensor. Now, the question is, why is it called a tensor and why not just a matrix? This is the very most important aspect of tensors. If I change my coordinates, so when you say that this electric field has these components x, y, z, it means that I have some coordinate system. And so here that coordinate system, for instance, is like this. Right? X is in this direction, y is here, z is here. This is my coordinate system. With respect to these coordinates, I'm defining x, y, and z. But the thing is, you can always change your coordinate system. You can change it to something else. You can perform some arbitrary rotation, and you can get some x, y, and z like this. We call it x prime, y prime, and z prime. Now the thing is that when you perform this rotation, the components of the electric field and the current will change in both of these coordinates. So as a result, these components of the conductivity tensor should also change. But how should they change? They should change in exactly such a way that this relationship between the conductivity tensor, the electric field, and the current density should be preserved. So what we want is that in the new coordinates also, the prime coordinates, this relationship should be the same as in the original coordinates. This is possible only if this matrix sigma under the coordinate transformation, it transforms in this way. So, and these matrices, what are these matrices? This is the inverse of the Jacobian. These are lower indices. Lower indices are covariant indices. They transform according to the inverse Jacobian. And for each index, you have one copy of the Jacobian. So such an object is called a tensor. And tensors are absolutely important in physics. Without tensors, you cannot write equations. You cannot do physics in a coordinate independent manner. So again, the rest of this is all like algebra, and not going to go into all that details. Then I give you another example of a tensor, which is called the moment of inertia tensor. It has the same properties. Under a rotation, the moment of inertia tensor transforms like this. So this is the same transformation property as for the conductivity tensor over here. So it might seem that this is two matrices multiplied by each other and then multiplied by sigma, but that is not the case. Because if you look at it carefully, you can write this expression in the following way. You can write it like this. You can put dxi prime over here, then sigma ij, and then dxj prime. So this can be written as some, I'll call this lambda, lambda I prime, sigma ij, and then lambda transpose, and lambda transpose becomes this. So well, let me just write it as this jj prime. So now, because of the order of indices, you have to put a transpose on one of these lambda matrices. And because lambda is an orthogonal matrix, it has to, the transpose is equal to the inverse. So these two expressions are the same. Okay. For the case of Lorenz transformations, the condition is a little bit subtle, because lambda inverse for some velocity is equal to lambda minus v. And that's not exactly equal to the transpose. Okay, so whenever you have an arbitrary relation like this, matrix valued components, such an object, such objects are, for instance, called p-type tensors, q-type tensors, and this is called a PQ tensor. P is the number of lower covariant indices, Q is the number of contravariant indices. Then we come to the concept of, by the way, you guys have a class at 9? MSc people? I am asking a question. Can somebody please?
So we have class at 9.
Thank you so much. So now we come to the different possible tensors in relativity. The first tensor is the velocity tensor. Well, the first one is the coordinate, the 4 vector. That is a rank 1 tensor. You can also define another tensor, which is called the velocity tensor. Well, the velocity 4 vector. And it is written in this way, dx mu by d tau. What is d tau? D tau is the proper time of the observer. The proper time is related to the time of the external observer in this way, according to time dilation. So the forward velocity of an object is given by this expression. And if you transform to a different set of coordinates, the forward velocity is given by the same expression, but with respect to the new set of coordinates. Then this forward velocity has some nice properties. Its norm is always constant. It's always equal to -1 when you set c is equal to 1. So the velocity is always a time-like vector. And then there are all of these identities which you should be able to derive if asked to do so. Then there is another very nice property of vectors. And whenever you have any two vectors, and you take the inner product of those two vectors, because the inner product is a scalar quantity, that scalar quantity is invariant under coordinate transformation. So if I look at the inner product in one system, one coordinate system, and another coordinate system, they are both the same. This fact can be used to derive this identity, which relates the Lorenz factors of two particles moving relative to each other and with respect to some external observer. So if the velocities of the particles with respect to the external observer respectively are u and v, so these are the Lorenz factors of the two particles. Now those two particles will also have a relative velocity. That means if you go in the rest frame of one particle, the other particle will appear to be moving with that velocity, right? That is w. So this is you can call it the relative Lorenz factor, and this expression can be derived by using this invariance of the inner product. And the fact that when you go to the rest frame of any particle, the forward velocity becomes just a constant, which is 1, 0 or c, 0. Then you have the velocity addition law, which I showed you briefly, can be written like this. And right, then we had a problem review session, right? Exercises from the back of the book. And so these problems, you should know how to work with them, right? So this kind of an algebra you should be able to work with. Also, one thing I want to stress very, very, very clearly: there should be absolutely no copying, no cheating on the quiz. If I have the slightest indication that anybody has done that, I will immediately report that person to the Dean of Academic Affairs. And I'm compelled to make such a strong statement because of what I've seen in previous tests in other classes. So I would like to believe that all my students are very honest and honorable people. But it turns out that given the circumstance, humans are very wicked. So the moment you close your eyes, the worst of humanity comes out. So Zoom is perfect for that, because in Zoom, I'm not watching you. So for Zoom, all of you, please remember, you will have, for the quiz, please remember, all of you will have to be on Zoom, and all of you will have to keep your videos turned on through the whole quiz, okay? Otherwise, you cannot take the quiz. So, okay, so this is, I've done a review of basic relativity. You can define a 4 acceleration. There are certain properties of the 4 acceleration and so on and so forth. These were more recent topics. Hopefully you remember them. And then you have this energy momentum 4 vector. So the syllabus will be up till the energy momentum 4 vector. Actually, I'll keep it till that. The syllabus will be till here. That is till lecture 10. Whatever I had covered till lecture 10. Okay. The remainder of the material up till following lecture 10, Doppler effect, optical appearances, so on and so forth. These topics will be on the forces. These topics will be on the midsem. Okay. All right. Then I've given you some homework problems. This homework problem set will be due sometime next week, and I'll give you some more problems before that. Okay. All right. So if there are any questions, please ask. Okay. Otherwise, I guess I'll stop the recording and the streaming.